So let's explore another example of finding the common area between two polar curves. So in this case, we are going to use a circle, which is r equaling to the red curve there, and a rose petal curve for sine of 2 theta. So let's work smarter, not harder here. So the overlapping area is going to be this stuff in here between the red and green curves, and we have 4 of those sections and they're identical. So let's find one overlapping section and then just multiply our answer by 4. So the first thing we need to do is figure out what those intersection points are, and we're going to work in the first quadrant. So let's find where these two angles are at. Now we have a graph with some lines on it. They look like they're directly on the lines, but let's verify that. Okay, so if I set 2 equal to 4 sine of 2 theta, we're going to get 1/2 equals sine of 2 theta. So sine is equal to 1/2 when the inside, so 2 theta is going to equal to pi over 6 or 5 pi over 6. If I divide those by 2, I'm going to get theta is pi over 12 and 5 pi over 12, which are both inside the first quadrant, so these are our two intersecting theta values. Which we can also tell from the graph here because the first quadrant is split into 6 sections, so each one is worth pi over 12, right? Pi over 2 divided by 6 sections. This is 5 pi over 12. Now the complicated part of this is it's not just going to be one integral. So if we look really closely, I'm going to zoom in really far on this graph, right? If we go from the pole to our first intersection point and pole to our second, right, the radius line actually changes. So in this bottom section, right, we're going for the green graph, whoa, that's a tongue twister, right? So we're going to use the 4 sine of 2 theta equation as our r value there, but in the green section in the middle, the gray section in the middle, right, we're using our r equaling 2 equation. And then we go back to another sliver at the top in our green section. So now those two little slivers outside of the yellow lines in our shaded area, they're the same, so we can actually just find the area of one of them and double it. So that's what I'm going to do, right? We want to do less integrals than we have to, especially because we are doing this by hand. So my area of one intersection, of one overlap, right, in the first quadrant is going to be A equals 1/2. Now I'm going to do the triangle part first, like with the red curve, so the middle part, the gray part, that's going to be 1/2 from pi over 12 to 5 pi over 12, our intersection points of my radius squared. So in that case, I am using the r equaling 2 equation, and then I'm going to add that to 2 of my 1/2 times my integral of, now we have to figure out where this curve starts over here. So the green curve, it's the wrong shade of green, right? The green curve, we want it to come up here, right, to that pi over 12. So we have to go smaller than pi over 12 to go backwards. This is actually the point where theta is equal to 0, right? If you plug in 0 to 4 sine of 2 theta, we get sine of 0, 0 times 4, we get back at 0. So we're going to use 0 to pi over 12 there as our limits of integration, and then we are going to square out 4 sine of 2 theta all squared. Okay, so if we simplify the first part, that one's really easy to integrate, right? We get 1/2 times 4 on the inside, so that's 2. Integral of 2 in terms of theta is 2 theta. And we are going to integrate that from pi over 12 to 5 pi over 12. So we'll take care of that arithmetic in a little bit, right? The 1/2 and the 2 here cancel out, and we're going to get plus the integral from 0 to pi over 12. If we square that out, we're going to get 16 sine squared of 2 theta, d theta. Okay, so let's go on. So if we do 2, we're going to do 5 pi over 12 minus pi over 12 there. And we'll simplify that in the next line. Plus, we get the integral from 0 to pi over 12 of 16. Now, we want to replace the sine squared part here. So we're going to use that double angle formula from cosine. So remember, cosine of 2 times whatever is inside, so I'm going to use u here, is equal to 1 minus 2 sine squared of the original angle. So if we rearrange that, sine squared of u is equal to 1/2 of 1 minus cosine of 2u, 2 times the angle. So we need to be careful here because we already have 2 theta on the inside. So whatever is in here, we're going to double it when we put it over here. So we're going to get 1/2 times 1 minus cosine of 4 theta over here. It needs to be double whatever's inside the sine squared. So we're going to go ahead and replace that into our integral. And then we'll keep simplifying from there. Right, so we get 5 pi over 12 minus pi over 12 is 4 pi over 12. 4 pi over 12 is pi over 3 times 2 is going to give us 2 pi over 3. Okay, so that part's done. Plus, we got 16 times 1/2 is 8. I'm going to distribute that and break it into 2 integrals now. So I'm going to get the integral from 0 to pi over 12 of 8 d theta minus 8 times the integral of 0 to pi over 12 of cosine of 4 theta. Why do I keep saying pi today? Okay. Okay, so we're going to keep bringing down that 2 pi over 3. Now, integral of 8 d theta, right, we're just going to do 8 theta from 0 to pi over 12 minus, okay, so now let's do some u substitution. So we're going to substitute in for the 4 theta. So my du would equal 4 times d theta. Well, that tells me that, right, 1/4 du is equal to d theta. So I'm going to get minus 8 times my 1/4 integral. Now I'm just going to replace my limits of integration here. So 0 times 4 is 0, and 4 times pi over 12 is pi over 3. And then we've got cosine of u du. Okay, so this is going to be 2 pi over 3 plus, that's going to become 8 times pi over 12, so we get 8 pi over 12. We can reduce that in the next line. That's going to come minus 2 cosine of u evaluated, I'm sorry, not cosine of u, sine of u. Forgot to integrate there for a second, from 0 to pi over 3. So we are going to add those. So that's 2 pi over 3 plus 8 pi over 12 is actually 2 pi over 3. So we get 4 pi over 3 here, right, from combining these two things. Minus 2. So sine of pi over 3 is root 3 over 2. And it's going to be minus 0 for sine of 0. So our overlapping for one region, so the one in the first quadrant, is going to be 4 pi over 3 minus root 3. Right, so a lot of work. We just found the area of that one shaded in region, and now we want the total common area. So the total overlap is going to be 4 of those. So we're going to do 4 times 4 pi over 3 minus root 3. So we're going to get 16 pi over 3 minus 4 root 3 as our final answer there.